Okay, so welcome to our last week of Collage course, and for the last week we have two very interesting talks, very important talks, and during the whole course we were trying to tell you something about the DKIST and how you're going to use it for your science and so on. But we are all aware that maybe ground-based telescopes and high-resolution things are not your thing. Maybe you're doing something else. And also maybe optical and near infrared and so are not your thing. Maybe you're interested in something else again. So what we're going to have this week is we're going to have two very special talks about synergies between DKIST and other state-of-the-art missions, as Gianna named them here. So today we're going to have Gianna Cauzzi from NSO, who's going to tell us something about synergies between DKIST and some other, well, let's say chromospheric missions. So yeah, we're gonna have that today, and then next on Thursday we're gonna have David Malaspina telling us about PSP. So yeah, everybody enjoy. Gianna, go ahead, and thank you so much for taking the time to give us this talk.
Okay, thank you, Ivan. Good afternoon, everybody, and I hope you're well. I don't know if you're happy or not happy that the course is finishing, because then I don't know if everybody's still home. Don't know what we'll do. But anyway, so the title, I took it from the webpage of the course. So this is something that Ivan had in mind already from the very beginning. And of course, we don't have yet the DKIST observations. We hope that we will have them very soon. And when it was possible and good to do, I put some examples of synergies between state-of-the-art missions that I will describe today and other ground-based telescopes, in particular, you know, the DST or the SST. Telescopes that observe invisible, that do polarimetry and things like this. So today, and please let me know if there is something that doesn't quite work with the screen, because I cannot see you, I just see my presentation. So today I will be mentioning something about two state-of-the-art missions. One is IRIS and one is ALMA. And the two, in a sense, could not be any more different, because IRIS is a satellite that works in the near UV and far UV. It's a spectrograph. And ALMA, as everybody probably knows, is a radio interferometer, which is ground-based, and it is a big, 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 big instrument. So I have put here a few details on how they, you know, their characteristics, their spectral range, their cadences, and so on and so forth. I don't want to go through them all, kind of boring in a sense. When I will be giving some examples, these things will pop up directly. So IRIS actually stands for Interface Region Imaging Spectrograph. It's a spectrograph, much like the one that Ivan has described in his course, much like a WISP would be on DKIST. This is a slit spectrograph. And if you want to cover a larger field of view, you just do a raster. You step the slit over the image and you create a raster. It's got a fairly high resolution because it goes to a fraction of an arc second, so that's pretty good for a UV telescope, because the UV telescope tend to be small, at least for the solar case, and this is indeed the 20 centimeter telescope. But anyway, I'll get back to some of these characteristics later. So I put here in red that they are both telescopes, meaning that contrary to what Valentin described last week, for the Parker Solar Probe in particular, that measures physical quantities in situ. Here we do observe, we acquire light, and we interpret the light that we acquire in terms of physical properties of the plasma that emitted the light. So the actual, what the course that Ivan had was really about. So this is a slide from your very first lesson. And this is the thing that I was saying, that looking at the light that comes from the atmosphere of a star, you actually get a lot of physical information, sometimes even about things that are inside the star and you cannot really see. And on the right here, there is a very grossly out of scale representation of the atmosphere of the star, where you have the photosphere, which is the surface, and then as you go to the very hot corona, million-degree corona, you pass through the chromosphere, which is this sort of enigmatic intermediate layers. And both IRIS and ALMA are well suited, mostly suited to study the solar chromosphere. So now I hope that this is not too redundant in a sense, but I thought I'd put in a few slides about reminding you why the chromosphere is important and why the chromosphere is difficult to study. And, so, and even you interrupt me if this is again too obvious or something. So the first thing of the chromosphere is that it shouldn't be there. On the left side, there is a model. This is from a paper of Matt Carson in the 90s, where he showed the run of the temperature as you move away from the surface of the star. So you see here on the X scale, you have your, by now, very well-known log tau 500. So log tau 500 equals 0 is the actual surface. So this part would be a little bit inside of the star itself. And then you go towards the outside, towards interplanetary space. Now, if you only had, the convective motions that we know exist at the surface and the radiation that is emitted, this would be the run of the temperature. You would have something that goes down in a monotonical way and eventually goes down to whatever the interplanetary space temperature is. If you instead do inversions like Ivan has taught in these past weeks, and you look at a variety of diagnostics, in this particular case, mostly continuum, different wavelengths, you get that the run of the temperature appears to be rather different than this. And this is also hinted at this particular part of the plot in the Carson paper. These are the famous valve models from Avrat et al. In the early 80s. And the scales, the X scales are changed, but the run is always the same. You start from the surface on the right and you move towards the outside on the left. This particular one has it in kilometers, like only the models can do, because we know, and Ivan has told you many times, that this is what you can get out, really. And so you see that the run of the temperature is quite different. It decreases up to, say, 4,000 Kelvin at some 500 kilometers above the photosphere, but then it increases again. It increases again, and it stays fairly high, 6,000, 7,000, 8,000 kilometers for quite a long span. This is 1,500 kilometers or so that correspond to about 10 scale heights at this temperature. So there is something, then we don't know what it is, that inputs energy, and this energy goes into heating this upper part of your atmosphere once you get away from the photosphere. The fact that the temperature remains more or less constant for a long span is due to the fact that most of that energy goes into ionizing hydrogen. You have a lot of hydrogen in a star's atmosphere, and most of that hydrogen was neutral at this temperature down here. So you have, you can put in a lot of energy. The chromosphere essentially acts as a thermostat and absorbs all this mysterious energy that probably comes from some sort of magnetically mediated input. And, and uses it to ionize most of the hydrogen present in the atmosphere. This further on the right gives you the mass, the column mass essentially. And from here, but we will see it better in the next slide, you also get the sense that the chromosphere becomes very, very tenuous. Indeed, and now, sorry, but the plots are with the axis oriented in a different way, so that now we have the surface on the left and the outside on the right. So again, this is the run of temperature in one of those models I showed before. And these are some simple derived quantities that express what I've been trying to say in words. The fact that the densities go down by 6, 7 orders of magnitude from say the beginning to the end of the chromosphere. The fact that the plasma becomes essentially ionized. You go from an ionization fraction of 10 to the minus 4 down here, all the way to about 1 at the top of the chromosphere. And also something that was not in the previous plot, but that we know it exists, that the magnetic fields also falls off with height, but it falls off in a much slower way than this very steep decreases. So essentially in the chromosphere is the place where you have a reversal of relevance, that at the bottom of the photosphere you have that plasma dominates whatever magnetic structures are there. As you get to the chromosphere, the opposite becomes true. So here is in words what I've just shown you in the plot. The fact that we have this very tenuous gas also means that you go further and further away from the LTE condition of the photosphere, because those require very strong, a large number of collisions. And so in your equations, your epsilon becomes smaller and smaller, and your source function becomes further and further, goes further and further from the Planck function. So that already creates a lot of complications in understanding it. Second, with a tenuous gas, also the dynamics deviates strongly from hydrostatic equilibrium, as the perturbations can amplify strongly, for example, waves, and I'll show you a couple of examples. And then the thing that I was just mentioning about the dominance of the magnetic structures of this. This is where the magnetic fields start dominating the game, really. And we haven't yet really understood very well how to, how to analyze that. Also because measuring the magnetic field in the chromosphere itself is rather difficult, as I think also Ivan has tried to show you. So this is an example. This is a movie that has been shown several times. This is the H-alpha line, which is a typical chromospheric signature. It's the Balmer line of hydrogen, neutral hydrogen. And as you move from the wing to the core of the line, you sample different parts of the atmosphere, much closer to the photosphere down here in the wings. And as you go to the core, you go further high up into the chromosphere. And again, I think that, that Ivan had this favorite saying that different wavelengths look at different layers. Indeed, I mean, this is very, very clear in this particular movie, as you go into these monochromatic images that are representative of the very different layers in the atmosphere. You see all these magnetic, something that looks like a magnetically dominated plasma, although we really don't know too much about the field in this linear fibrillar structure. An example in terms of the dynamic that goes into place in the chromosphere is here. This, you know, you have a lot of oscillations, acoustic waves that are excited in the photosphere by the convection motion. Some of them can propagate all the way to higher parts of the atmosphere, in particular the ones that are with the frequencies above the 3 minutes. Sorry, so a period which is shorter than three minutes. And they do stiffen, and eventually they do shock, and they dissipate in situ some of their energy. This has been modeled by Carson and Stein already in the 90s with their seminal paper on the so-called bright points of the calcium lines. And this is a more modern version. This is another typical chromospheric signature, which is the calcium-2 8542 angstrom. And this is a plot of the spectrum versus time. So you see that periodically you have this, I think it's called sawtooth pattern, where you have this brightening that coincides with a strong and sudden blue shift of the line, and then a more softer, how do you say, slower falling into the red part of the line, and then the things repeat. And when you look at it in the core of this line in time, This particular kind of spectral distribution in time correspond to these little bright points that you see in some of these images you see inside in the internetwork, far from the magnetic areas actually. And so, and those correspond to actually places where you have a bit of an enhanced temperature and density, which correspond to dissipation of your acoustic shocks in the chromosphere. Okay. Another quick reminder about the chromosphere is the fact that with respect to the photosphere, since the physical conditions change so much, we also change diagnostics. In particular, we move away from the mostly neutral diagnostics that we use in the photosphere to ionized elements. And since the gas is so tenuous, in order to see something, you need spectral lines that correspond to transitions that are very probable. And that can happen, for example, if you have very abundant species, and indeed hydrogen, in particular hydrogen, the Balmer series of hydrogen is something which is a typical signature of the chromosphere, or the resonance lines. The resonance lines are the strongest lines because they correspond to the transition between the first excited state and the ground state of whatever element you're looking at. And then there's, of course, 4 elements that are also relatively abundant. So in the visible, honestly, we are left with not much if we're going to look at the chromospheric diagnostics. We have the Balmer lines of hydrogen that, as again, he has been showing you, Ivan has been showing you, these are very, very strongly scattering. So as far from LTE as you might fear. Some lines of helium, helium-1, neutral helium, and then we have the resonance lines of calcium-2 in the far blue and the subordinate triplet in the infrared, which corresponds to the plot that I just showed you. And actually here, this is the contribution function of one of the lines of the infrared triplet. As you can clearly see that the wings sample down in the low and mid photosphere, and then you have this sharp transition to the core of the line that samples the higher layers, so say something that we call the middle chromosphere. So, opposite to that, in the ultraviolet, there is an abundance of lines that correspond to chromospheric, that are chromospheric diagnostics. Indeed, most of the resonance lines are UV wavelengths. For example, the one of hydrogen, of carbon, of several states of ionization, magnesium, the same of silicon, and so on and so forth. I repeated silicon twice. So the UV is a very, very profitable place to go hunting for chromospheric diagnostics. And we finally stop with this very long introduction, and we get to the iris and those diagnoses. This just for some historical knowledge is an atlas that was compiled by Kurt et al. With Sumer. Sumer was a UV spectrograph on board the Soho, has been working for many, 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 many years. There's a lot of very nice work done with it, but just to give you an idea, a sense of what kind of spectral lines you are looking at. In this particular range, which corresponded to the FUV, the far UV range, one of the far UV ranges of iris, you have the strongest lines are actually transition region lines, so formed at hotter temperatures. That is the silicon 4. These 2 lines, this is an oxygen 4. But then if you go here, there is a forest of lines that could be used for chromospheric and also some photospheric physics. If you go into the iris kind of data, this is the data that you obtain, where this FUV2 is the same range that I was showing before from Sumer, where the strongest lines are the silicon 4 resonance lines at 1400 angstroms. And the other, the so-called FUV1, which is a slightly shorter wavelength, is around 1330 angstroms, has the strongest lines are the resonance lines of carbon 2. Now here, this particular data, It's not maybe the best because this was taken at the limb, so the signal is not super strong. But here you will have a lot of other lines that you could use. Of course, if you wanted to make those weaker lines to be more prominent, you have to expose for longer, and your cadence will suffer. But anyway, this is the kind of trade-off that you have to do all the time. This is something that might look much more familiar, and this is the near UV. So this is a range around of about 50 angstroms around this wavelength of 2800 nanometer. No, angstroms, sorry. With the resonance lines of the magnesium-2 and a bunch of other chromospheric and photospheric lines that you can see, as well as some continuum windows that are very, very useful. Now, the magnesium-2 system, you know, the resonance lines, there is the system of the triplet of subordinate lines, like for the calcium-2, the two elements are essentially equivalent. They are on the same position in the periodic table. And the triplet system of the magnesium-2 actually falls in the same interval. It's actually, these are two of them, and the other one is here. This is kind of interesting, so that you have both the resonance and the subordinate in the same wavelength interval. Sorry. The magnesium, magnesium-2 is the dominant state of ionization of magnesium throughout the solar atmosphere, pretty much. And magnesium is actually much more abundant than calcium, and so these two lines are the strongest, together with Lyman alpha, have the strongest radiator in the chromosphere. If you wanna take a look at the data that IRIS provides, it's very nice. This is the website. I had planned to go and check on this, or do you think this is redundant even? I wanted to show them some, you know, the data, how you get it, and so on.
I think it's a great idea. Yeah, I mean,
okay. So let's start. So I mean, the website is here.
Pretty useful.
Okay, the website is here, and I think, let's see if I can now. What do I show? Now you see myself, correct?
We see your PowerPoint.
You still see my PowerPoint? Okay, so let's see if I can get this one to share. How do I change? Oh, I have to stop sharing. Yeah, new share. This one. Oh. Share.
Yeah.
That okay now?
Yes, this is very good. Yeah, we see your browser.
Okay, so this is the actual web page that I gave you. And this is what it looks like. It's very, very nice, very complete, a lot of information. And so if you want to have a sense of the data, you can go, for example, to recent observations. And it starts with the most recent data that has been acquired. And you have, for every observations, for every observing data set, you have this kind of summaries where it tells you the title, and from the title you have a sense of what physics they wanted to do, where they pointed, what kind of field of view they were observing, and so on and so forth. An interesting one is, for example, the kind of cadences that you can get. This is a sit and stare. That means that the slit is here and stays there. And so you see that the cadence is 9 seconds. That's not as high as we would like to go, or what we hope to go with, you know, ground-based instruments. But of course, you have to think that you have a 20-centimeter telescope and not a 4-meter, for example, that the UV radiation is not much. We're still, you know, in the slope, descending slope of the Planckian there, even if you have emission lines, they're not so super strong. And also that the efficiency of the telescope and instruments in the UV is much less than what it can be in the visible, given the optics and so on. So, you know, this is actually fairly good. This, I went to a particular kind of observations, and this is what you get from one. If you click on one of those, these were at the South Pole, the one that I was showing before. So this is a slit jaw, because IRIS has a set of 4 slit jaws images, much like, say, the DISP will have by using the VBI at the same time. And these 4 slit jaw are at 4 wavelengths. One is next the carbon-2 resonance lines, one next the silicon-4 resonance lines, one next the magnesium-2 resonance lines, and one in the continuum. And this is the same spectra that I showed you before. So you can browse the data, and you can also get movies of how this thing evolves during the observations. It's actually very, very nice. So, I mean, I don't know, from the movie probably doesn't show very clearly, but it is evolving, you know, while you move the slit. You see that this one moves because the slit is always on the center of the field of view, correct? No, I'm saying something wrong. Right, in order to do the raster, they move the image on the slit, jaw. It's also the slit jaw. It seems like it's moving, but it's... Okay. So I will go back to this one now. Let's see. Now I can do this. Share screen. Yeah, sorry. Take some time. Okay. Do you see it? Okay.
Yes, we do.
Okay, excellent. So some results and some ideas for what could be done further, you know, to increase our synergies. And so this is a I don't know why there are those red things together here. I didn't see them before, but anyway. I think I deleted by mistake something that needed to be written here. Okay, I will explain it. This is some modern revisitation of the work that I showed you before about the acoustic shocks that we had done some years ago with the calcium-2 8542 line. In this case, this has been done using IRIS and using contemporary observation from the ground, in particular from the Swedish solar tower. So here are the slit jaws around the carbon-2 resonance lines. This is the slit jaw around the silicon-4. This is the slit jaw around the magnesium-2. And this is the same field of view observed with a broadband filter in calcium-K. Calcium-2K, and this is CRISP in H-alpha, CRISP in calcium-2 8542. The original idea was to see whether these shocks that we know exist in the mid-chromosphere, whether they had any signature at higher temperatures. For example, looking at something that happens, say, here in silicon-4. In equilibrium, the silicon-4 would form at around 80,000 Kelvin or something. So you can see a clear correspondence of bright structures from the core of the calcium-2 8542 and the slit jaws, even if it is a little less clear for the magnesium, but it is fairly clear for these other 2 slit jaws. But now the nice thing is that they have the spectra to go and take a look at what's happening really in those positions. So the spectra were in, I don't know exactly where in this field of view it was positioned, but these 5 are the same as the temporal stack that I showed you of the 8542. So this is actually 8542 for about 5 minutes. That one before was of the order of an hour or so. So what I described as the sawtooth would have been, you know, here, something like this, and so on. This is a very blown out portion of that. And you have a correspondence, you know, you can sort of infrared, in H alpha, and so on, it appears to have a clear signature in the wings of the magnesium-2, sometimes in carbon-2, sometimes certainly not in silicon-4. So the conclusion of this work, now this is just one example, but they had many because they had a lot of time in it, was that yes, these shocks exist. They are, however, confined in the mid-chromosphere to temperatures that are not that far, from the usual 10,000 Kelvin or something like that. And because you don't see them in hotter lines, sometimes you see them in this one, but not often. So the question is, why are these slit jaws that are centered around these hot lines showing it so well? Well, the fact is that most of this emission is really continuum, which is continuum at, this is a broadband filter of several angstroms. The lines, unless you have something very explosive, do not contribute for much into this broadband. So essentially, you're looking at the continuum at about 1400 angstroms or so, 1300 angstrom, which is formed in the mid-chromosphere. So everything seems to be fairly consistent to before, with the conclusion also that they don't get any hotter. So they might be able to heat locally the quiet chromosphere. Probably they're not very important for what we call the chromosphere heating problem as a whole, right? One of the issues that are still sort of people would like to go is why these shocks appear where they appear with that sizes, why sizes so small versus what we think would be the driver, which is the acoustic oscillation in the photosphere, which is probably larger than that. How does that happen? And so, I think that there will be further investigation of this kind of problem once we have, for example, the BTF and the DISP that can work together. And hopefully IRIS will still be there and help us in this kind of analysis. Oops, what happened? No, interesting, sorry. I've lost my, oh no. Okay.
I think your share maybe stopped spontaneously.
My share stopped, but I think that I've lost my PowerPoint. So hold on a second, that I retrieve it. Oh yeah, it did collapse, oh no. Oh, I'm sorry, guys. So if you have any questions in the meantime while I try to get it. I've actually lost the PowerPoint. Where did it go? There. Sorry.
Okay. Yeah, you can probably just restart it.
Yeah, I'm trying. So now I have 3 versions of it. Which one is the good one? I don't know. Okay. So try again. Sorry for the interruption.
No worries, no worries.
Too many windows. I get confused. So do you see it now?
Now we see it. Yeah, you just need to start the presentation.
Yeah. I don't know why that doesn't work, but anyway, let's try slideshow presentation. Okay. Can you see it?
Yeah, you just need to click swap displays again because we
Oh,
see
yeah, sorry, you're
we
right.
see the
Yeah,
other one. No worries.
there you go.
Yeah.
Thank you.
Before we proceed, can I just ask a question about the previous research?
Yeah,
So, so if I understand correctly, the point of this research was to look at uh, where the emission is high, right? And basically to discriminate between the layers according to the wavelengths that sample appropriate layers.
yeah,
So we are not interested in the velocities, for example, per se, because we could also characterize the shocks with the velocities.
correct. Yes. I think that here actually they're doing both. You know, the first one is they were interested to see whether the shocks would have a signatures at not higher level, but a higher temperature, really, because, you know, defining higher level is always difficult. The chromosphere might be 100 meters thick for what I know, and everything forms in the same place. So with higher temperature, that would give you a sense if there is, what kind of energies are involved. And the answer to that was no. You could characterize them with velocity, and that is what we did mostly with the infrared triplet of calcium too. And it is, you can see it also here. You know, you have the same hint.
Yeah, that shows that shows that characteristic sawtooth pattern, doesn't it?
Correct, correct.
Yeah.
It's
How
not.
come that's not present in carbon too?
That I do not know exactly. I have for the magnesium too, I think I have a sense that this interval is not enough to show it well. Carbon too, I don't know. I don't know. Could it be a noise issue also? You know, it's fairly noisy. This is quiet sun after all. That's a good question. I don't know. So you see a hint of the heating, but not much in terms of the velocity. Maybe the velocities are gone by then. You know, you've lost your signature. I mean, here it's the beginning of a shock really that you can sample in the calcium too. In our work, we did we had also photospheric signatures, and we did an analysis of the phases and the coherences between the oscillations in the calcium and the photosphere. And from the phase differences, you get that really you are about 1,000 kilometers above the mid photosphere. That was the kind of numbers that we had. It could be that if you could sample better higher up where you have less density, you know, you will see that better on one hand, but also the shock more developed. At that point, you are dissipating the energy there, and the velocity is not the main signature anymore. Okay, can I continue?
Sure, go ahead.
All right, so some other IRIS results that maybe are more familiar to the people that have taken your course is that, of course, we can use the magnesium too in particular via spectral inversions to derive the chromospheric temperature structure. And this is, as you can imagine, a kind of work which is being spearheaded by Jaime de la Cruz. That is being using his inversion code, the stick code. I don't know if you've described that one, but I mean, you've described the basic points of an inversion code of that kind. And so given this was using only the magnesium 2 lines, including the subordinate, and I think the continuum nearby, in order to derive the run of various parameters like the temperature, the velocity of the atmospheres that we're looking at, and the microturbulence parameters that we know is something that's always a bit of a mysterious thing that is there to accommodate your profile. So that depending, this is the plage, this is a sunspot, and I think this was the quieter sun, and so that you have a very different temperature structure in these different features. I don't know if I mentioned, but I say it again in case, IRIS does not have any polarimetry, so it would be very interesting to combine this kind of analysis on the one hand, maybe with other chromospheric signatures in order to have a better, more constraints, because you know that you can play a lot of games with your nodes and your fits and so on to derive these things, as well as understanding the relationship with the magnetic field. So this is obviously one of the fields where a synergy with the observations that the DKIST will be able to provide that is, something that we are looking forward. And then a third result, which in a sense goes in that direction, although not for large magnetic features, but for small things. This is a recent paper by Gianna Cauzzi, and some of you that were at the school in Northridge in January have seen some of this work. So they combined ground-based visible observations. These are your favorite spectral photospheric lines, as iron 1, 6301, and 6302. Actually, I think they have only one of them. And they do a weak field approximation. Actually, I'm wrong. This is a magnesium 1 magnetogram. In a weak field approximation, and they combine it with data from iris, including slit jaws and the spectra. I haven't shown the spectra here. The point of the work is that they follow all these very tiny magnetic features in time, and they have a long sequence of this. And they go and check where these features interact and cancel. I don't know, it's not very clear, but here there is some green thing where you have a cancellation. This is another one where you have a cancellation. And apparently these correspond to places where you see brightenings in these chromospheric signatures. Now this is a slit jaw. Of course, it tells you something, might not tell you other things. So they go and look at the magnesium 2 spectra in the places where they can, because the slit is only one portion of your slit jaw. And they do inversions, like I said before, like I showed before. They determine what kind of temperature and possible heating there is corresponding to these cancellation events. And what they find is that there is heating, but it is still too low to justify the global chromospheric heating again. Now, one of the things that could be is that at higher resolution, you see much more flux than what you see at lower resolution. This is something that has been, we know it to be. And again, that with the Zeeman effect, if you have something which is smaller than your element, you don't see it if it cancels out. So higher resolution and polarimetric sensitivity with DKIST kind of data could provide, again, further insight in this. Okay. Now I will move to ALMA, if there are no questions. Okay.
I have a question.
Yeah.
Is Iris, how long do you think Iris is going to be in orbit?
I don't know. Well, maybe Gianna can answer that. I think for a while still. Yeah.
Why do you think I could answer that?
Oh yeah, go ahead.
No, I can't. I have no more insight than you do.
Oh, I see. I mean, it's working well still. It's got a huge potential. We've seen it. These things take time to understand and develop. I think that a lot of the early works with Iris, especially in the US, has been on flares, because there is a couple of lines, both the transition region lines that become very, very strong during flares, but there is also one particular coronal line of iron 21 in that particular wavelength range that has been extremely useful to measure the dynamics of the chromosphere during flares, of chromosphere and corona during flares. So there has been a lot of work there, but then, active region declined, the flares went away, and now slowly people are using this kind of signatures more and more. And I think there's still interest in having it to combine with other, especially as we get new instrumentation on the other side, right? So I don't think it costs too much to keep it up. But again, I could be wrong. I would hope and expect that for the first few years of the DKIST, we still have it. Okay. So my second synergy was with this beautiful thing, which is called ALMA, the Atacama Large Millimeter Array. And I think that most of you know what it is, or at least know of ALMA. So ALMA is a set of radio antennas. So we go from the ultraviolet to the radio waves on the other end of the spectrum. They are positioned in the Atacama Desert in northern Chile at an altitude of over 5,000 meters. There is a different kind of antennas, and again, here I'm not super informed of the details, but you have the 12-meter antennas. There is 50 of them now that you can spread out and to do the very long baseline, all the way from 150 meters all the way to 15 kilometers, so that you can have a very low, very high spatial resolution, because that depends on the baseline. And then you have other antennas that stay in a more compact configurations called the compact array, that are used more for what they call total power, to do the, the flux calibration and such. The wavelength range is between 0.3 and 9 millimeters. I think that the 9 millimeters has been recently added, and that corresponds in frequencies at 30 to 950 gigahertz. So ALMA is a nighttime facility, right? We know that. That's why it was built. You can do a broad range of science, really, from protoplanetary disks to black holes. You might remember last year that there was that famous image, first image of a black hole, and ALMA was part of the set of instruments that had participated in creating that image. And here's a poster that was 2 or 3 years ago, I think, of protoplanetary disk, 25 of them, 26, how many are there, of all sizes and shapes and inclination and so on. It's just very nice. The spatial resolution that I was mentioning before can go up to 4 milliarseconds. The formula is below. It's 0.015 seconds per lambda in millimeters. So that is the most that you can do. ALMA can look at the sun. And actually, that was in the design from the very beginning as a sort of, I remember talking to one of the ALMA guys many years ago, and they said, well, you solar guys are cheap, right? So with just a few technical modifications, say, they could ensure that also all the solar astronomers will be part of the enterprise, and so on. That it was always helpful to have part of the community that works with you instead of against you. So that was good. But anyway, ALMA has been offered for solar observations since late 2006 in a sort of a limited configuration with respect to what they do for nighttime. So for now, it's only 2 bands. Band 6 and band 3, so around 1 millimeter something and 3 millimeters. I think that the next campaign would offer band 7 as well, so higher spatial resolution. But for now, ALMA, like all the other big facilities, has been put on hold. So there is no idea when they will start observing again for the situations that we have all around the world. The maximum baseline, again, for technical reasons, for solar observations is of the order of 100 meters, so that the maximum spatial resolution that one can obtain is really of the order of a little more than half an arc second for band 6 and 1.6 arc seconds for band 3. So this has been kind of limiting for the things that one would want to do. With a certain spatial resolution goes a certain field of view. We've seen this many times during this course, so these are the numbers. I think that band 3 is actually 60 arc seconds. I might have written it wrong there. But you can go high temporal kilometers. And a little bit of trivia, this picture has been taken on April 23 of 2017, which is the day when Momo's observations were taken. So Momo is actually the expert on ALMA. You should ask him instead of me, all that comes to your head. So why is ALMA useful for the sun? There is a wide variety of science cases that one can think of. For now, I've limited myself to the easy one, which is the measuring the temperature in the chromosphere. There are other situations where radio wavelengths at these, or radio data at these wavelengths, it will be important, for example, during flares or for measuring strong magnetic fields in the corona or things like this. But anyway, at these wavelengths, the continuum, because we measure a continuum for now, the continuum is formed in the sun, is formed at chromospheric heights. And actually, in these wavelengths, it is very well behaved because it's due to free emission, mostly of an interaction of an electron with an ion with a proton. There is some contribution also of the same phenomenon with neutral hydrogen, but that is less relevant, again, for chromospheric, solar chromospheric conditions. So this is mostly the main opacities there. Now, since this process is coupled only to the local plasma conditions, there is no scattering involved, we are in an LTE situation, and so our source function is equal to the Planckian, which is always very nice. And since we are very long wavelengths, we can use the Rayleigh-Jeans approximation that so the Planckian can be written as proportional to temperature. So essentially, when you do your equations, you get that your intensity is equal to the Planckian essentially, and it is directly proportional to the temperature. Actually, the radio people always work in unit of brightness temperature, which is the temperature that comes out of this chain of approximations that I have been describing right now. In this work by Maria Lukicheva in 2015, she showed actually how that is a very nice approximation for the electron temperature, which is the one that we are interested in, and so on. And if you want to have this paper by Wedemeyer et al. Has some very nice description of all the physics that's behind this set of words that I've put here, so that you can verify it by yourself if you if you are so inclined. But anyway, so it's very nice. So I see an intensity, and if I can calibrate it, which is not trivial but can be done, then I know what temperature I'm looking at, right? And I know that I'm looking at the chromosphere. Yes, but where am I looking at? This is the result of a model that shows how the different wavelengths, much like we have the different wavelengths in the spectral line, like H alpha or so, that they sample different parts of the atmosphere. This should be read less as a contribution function graph, more like a distribution. So it's a certain model by Wedemeyer et al. And for any particular wavelength, they went and plotted the distribution of where that particular radiation was coming from in the model. So that you have very large, you can see a very large span covered at every wavelength, but there is this progression where you have that the longer wavelengths are formed higher than the shorter wavelengths. So that will be perfect, right? You go a different wavelengths with ALMA and you have all the run of temperature in your chromosphere. Maybe you can compare it with what you get from the spectral lines. So people were sort of eagerly waiting for this kind of data to appear. These were some predictions, again, from Maria Lukicheva. She's been doing the bulk of the work for what concern ALMA, solar ALMA, for until now, together with Steve White and Tim Bastian. And so here is a snapshot from the Bifrost simulation that everybody knows. And this would be the kind of intensity that you will get a different wavelength from 0.4 all the way to 10 millimeters. And this is the temperature, the electronic temperature that I was discussing before. And that is where that correlation came from, really. This is another expectation that's quite even older, 10, 15 years ago almost. This was taking the hydrodynamical simulation of shocks in the mid-chromosphere, as I have been describing already twice, and to see what would be seen at millimetric wavelengths. So this figure runs with time. This is, I think it's about an hour, a little less than an hour this way. And this goes with wavelength that, as we've seen before, should also be some sort of height scale. And you can see, I think you can discern that on the screen, that you have some perturbation that start lower and propagate, and you have this inclined thing, because as you know, to go higher and higher, these are acoustic waves, so it takes some time. And then when you get a certain height, you have what we were discussing in terms of dissipation of the shock, heating, local heating, and so on. This is a 1D model, so there is no spatial structuring around it. But the kind of delta temperature that you should be able to see, you know, it's a delta intensity that then you translate into delta temperature, it's fairly big. For example, 1 millimeter, 10 millimeter, you have this kind of, if you take just a slice here, you have a variation of, you know, thousands of Kelvin differences. So it should be fairly visible. This, as far as I know, was probably the most anticipated result of ALMA, but has not been confirmed yet. And I think that some of the issues are to do with the fact that the spatial resolution has been much less than what we were expecting. So it's currently is not trivial to do the two wavelengths. So you have to do first one and then the other, you know, for an extended period one and then an extended period the other. But especially the spatial resolution has been much less than what we were expecting, and that might have been an issue. You know, when you average over a lot of these things, you know, the shock is very small, and you average over a lot of cold thing around it, things don't become so clear. But anyway, some results. So here on the left, just to give you a sense, yeah, so these are chromospheric signatures. Is it true? Is it not? So it's a comparison of the full disk taken at band 6 and band 3 with the magnetic field, the full disk from HMI, and the AIA helium-2 emission. So you can get a sense that yes, it shows things that are typical of the chromosphere. It's, in particular, it is hot where you have strong magnetic fields. It's hotter in band 3 as you are higher. And so, of course, these have a spatial resolution which is much less than what I've been telling you before. Of course, if you want to do a full disk, it would take forever otherwise. On the right, there is, I think, one of the first comparisons at higher spatial resolution with IRIS. You know, since we've been, this is the day of IRIS and ALMA, so here they are together. And in this paper by Tim Bastian et al. In 2017, they took ALMA at band 6 here, this one, the 1-something millimeters, and IRIS in the magnesium 2H, which is a parameter of the magnesium 2 line. They should be formed in fairly similar heights or, you know, portions of the atmosphere. And indeed, the spatial correspondence appear fairly nice, fairly similar. When you plot the temperature that you derive from the brightness temperature of ALMA and from this parameter of the spectral line in IRIS, you get this kind of scatter plot, where there is several things that do not quite match. The first one is that the temperatures derived from ALMA are sensibly higher than the ones, the radiation temperature derived from the intensity in magnesium 2. And also that the correspondence between them is more or less good depending on the kind of feature that you're looking at. The yellow part is the plage, or, you know, these very hot parts, and they seem to go fairly well together. When you go into colder features, whether it is a spot, I think is the blue, or whether it is this, what they call the quiet regions, down here, the correspondence is not so obvious. So this is still being worked on. It's you know, the fact that this is not a full inversion. This is just taking a certain parameter of the line and translating it into radiation temperature. So certainly non-LTE effects will have a strong growth here, and we might require a full inversion to get some nicer results here. And actually I had something at the very end. Some of the nicest results until now, I think, is the one of Momo. Then again, I will be sailing through this, but he can explain you much, much better. So they had the coordinated observations that famous day that I told you before, and they had a bunch of chromospheric signature from the ground base, the DST with the IBIS. They had also IRIS, although IRIS has not been used yet in this work. I think that Ryan might be working some with that. And then ALMA was observing both band 3 and band 6, one after another, as I mentioned before. And so now, actually, his results come from H-alpha and band 3. And this is a comparison. Why would one need to compare these two things? Let me go back here. You remember this is the day that I also showed you that movie of H-alpha, going from the wing all the way to the core of the line, taken with IBIS. So you have an idea of the lot of fibrils that were in that particular region. It was a fairly, here you have a magnetic scene. So it's a fairly quiet, but apparently in all these, internetwork, I call them internetwork area, there were a lot of magnetic fibrils at the chromospheric level. So that if you would see this in the photosphere, this would be, okay, nice granulation and so on, but in the chromosphere, this would be mostly covered by fibrils of salt. And we had shown some years ago that the width of the H-alpha line appeared to be a good indicator of the chromospheric temperature. So now, since we know that ALMA is an indicator of the chromospheric temperature, the obvious thing was to go and take a look and see whether they make sense one another. And so on the left, you have the width of H-alpha at the native resolution, which was very good. It was of the other 0.2.3 arc seconds. And on the right, you have a snapshot at the same time of the ALMA in band 3. As you can see, the resolution is sensibly different. So much so that oftentimes it's not trivial to understand if you're looking at the same features. What Momo did and was very nice was to show, and I don't have here, I think, the degraded resolution of this particular image, but if you squint your eyes, you can see that the things do correspond pretty well. And yes, we're sure that this is indeed the field that we were looking at. And so if we plot a scatter plot like Bastian et al. Did with the magnesium-2, we have this kind of scatter plot. So, okay, first result. We have apparently a very good correlation between the H-alpha width and the brightness temperature measured by ALMA in band 3. This seems to be maybe better. This is the regression line, the red dashed one, and the blue dots are the results of modeling. Momo took some 1D models of Fontana et al. 2011, I think, and calculated both the ALMA radiation and hence temperature and the H-alpha profiles and hence width, and plotted them up here, so they seem to go very, very well. So we seem to have a very nice correlation between the two, which is good. But then the question comes up, obvious, is why do we have this correlation between something which is pure LTE, like we have been discussing till now, which is the ALMA intensity, and something that characterizes a line which is as far from LTE as you can imagine. And I think that the nice results of this paper are summarized here. And again, Momo, excuse me if I don't explain it super clearly. The reason in it the reason behind the correlation is that both ALMA and ALMA band 3, intensity in band 3, and the H alpha profile depends strongly from the population of the n equal 2 level of H alpha, which is in this particular plot. So this is the density of atoms in the excited state n equal 2 in those models with height. These are the models that we were discussing. And these symbols here represent the height at which tau equal 1 occurs for the core of H alpha. I think it's the dot. And for the radiation of 3 millimeters, which is the triangle. So you see that there is a correlation between these things. In particular, for the hottest models, which are this one here, and which are represented down here, these positions really coincide. So that the line, and especially the width of the line that depends on that parameter, are the line H alpha and the intensity at 3 millimeters are formed in the same part of the atmosphere. This thing is more true the hotter your model is. And these are contribution functions. So I don't know if you can see it very clearly. Here is the usual wing of the line down in the photosphere. And then you have this diffuse area where you're forming the core from which you calculate the width. And for the hotter models, that becomes much more limited to this particular layer of a certain height, which is the same where you have the most emission from ALMA. So one thing here was the correlation was explained, but another important thing that comes out is that ALMA, as we've seen, really gives you the temperature of the chromosphere, but you really don't know where that temperature comes from, in the sense that it could be here or here or here, depending on the feature that you're looking at. So it's the usual story that there isn't a layer of a chromosphere, but there is a very corrugated surface, and you not always know where you are. So that is a very big caveat that one has to keep in mind. And this kind of feature would be very nice, sorry, this kind of study would be very nice to try to repeat, for example, with different kind of features. This particular field of view had a lot of fibrils. So I've seen it, what is it here? Had a lot of fibrils, maybe in a quieter area that would be interesting to look at. And by the way, the fact that nobody, at least to my knowledge, has yet compared the presence of shocks, or checked for the presence of shocks in the ALMA time series, I think has to do partly to the resolution that you can see here is not very great, and partly because a lot of the chromosphere that we sample with this band 3 and band 6 is these fibrils, that they cover even things that you wouldn't suspect are covered by fibrils. But anyway, let me go towards the end because it's already too late. This is, again, a very recent paper, again, by Maria Luticello, of something that I have called dark holes. In 2 words, they have tried to combine several diagnostics of the chromosphere, and you can see ALMA band 3, there is AIA, different wavelengths, there is IRIS, and there's also H alpha, although this H alpha is not a spectrally discriminant, this is a broadband from Gong. And I see these particular features here that are fairly dark. They are much darker than what they call the quiet sun, for example, here, right? While, for example, in AIA at the helium-2, 3, or 4 angstrom emission, you have dark things, but this part is as dark as that. This does not appear to be the case for ALMA. So they call these are about 60% of the temperature of the quiet sun, of the intensity of the quiet sun. So they call these things the chromospheric ALMA holes, because we like to give new names to everything we see. And they speculated that they might be related to the presence of cold pockets in the chromosphere that might occur, below the magnetic canopy, below maybe the shocks where you have adiabatic cooling, and there might be the places where the famous CO lines of 4 microns form. So obviously a primary science use case with DKIST would be to coordinate these kind of observations with the cryo-NIRS on disk, looking indeed at the CO lines. And quickly, I was mentioning before the fact, oh, wouldn't it be nice to use ALMA to do inversions? And these people have actually done just that. It's a very recent paper of a couple of months ago. So they have a very, very nice coordinated set of data from the magnetogram. This is both HMI and Hinode. This is AIA in the corona. This is AIA 304. This is AIA, I think, 1600 or something. Oh, I'm not sure. No, maybe this is an iris slit jaw. And this is the iris magnesium 2. So I don't want to go into a lot of details, but anyway, people are starting to try to use ALMA, both as a check and as a constraint in the inversions, not via models, but via actual data. And these are their results that might be not obvious to explain. This is a very small portion of the field of view, right here and here. And this is, let's see if I remember myself. This is the continuum, which is the observed continuum here. This is the observed, I think, core of magnesium 2 or wing of magnesium 2. And this is the observed ALMA. This is band 6. Then the second of these series of 3 panels is what you would infer from an inversion using only iris, or what you would infer from an inversion using both iris and ALMA. So the continuum, I don't know if you have very big differences. The big difference that you see is here. Essentially that if you use only the iris magnesium 2 data, you cannot recover the actual observations of ALMA, the temperature in certain features that ALMA sees. While if you use both magnesium 2 and ALMA, you get there, not quite, but better. And they speculate again that this very cold thing that they see might be related to one of these cold bubbles in the low chromosphere, and that magnesium by itself really has no sensitivity to this kind of plasma. So again, the kind of prime science use case for a coordinated data set would be the same that I mentioned before. So this is the customary, very happy conclusion, but I thought that I would put this because I'm not an optimistic person to start with. So the opportunity for synergies is certainly there. How to plan iris observations. It's really, really easy. You call Bart. And essentially you discuss what you want. He tells you what you really need. And you agree on a date to observe. The data then, after it's taken, is available in a few days and is mostly fully calibrated. How to plan your ALMA observations? Okay, first of all, you have to wait for the ALMA proposal call that comes once per year. Then after you write it, you have the proposal, which is judged by a panel, which is mostly non-solar people. Then you have to wait for them to start observations for the proper configuration to occur. And that might take another year, honestly. Then you have to wait for the data center to deliver your data. And that might not be super fast. And then you have to fight a lot of vagaries of the data. Unfortunately, I think that for the kids, we're still like ALMA. So this will be the kind of process that our PIs will have to go through. But hopefully with time, we'll get to the iris mode called Bart and get everything done. Okay, I'm done. Share.
Amazing, thank you so much. These were some interesting projects here, and you know, synergies. So everybody, questions, comments, suggestions, inquiries.
Are you still seeing green?
Okay.
Where is this? Let's see, where is the Zoom? Yeah, sorry. Hey.
I have another question.
Sorry, Momo, I mistreated your paper. You can explain.
Oh, no. Well, first, Kevin was the driver behind this paper. But the thing is, if we want to use DKIST as we did in this coordination with ALMA and IRIS, is there going to be like a special pathway for submitting like these proposals where we're going to be like, oh, we have, because
that's a good question. The DKIST people are certainly very interested in getting these things done, so they are very they're ready to accept, say, special periods when these things should be done. Certainly, it's not trivial because, like ALMA, you have to change configuration, right? Maybe the configuration that you want is very different from what the rest of the world wants. So it will be, there needs to be some preparatory work also with the ALMA counterpart and make sure that you know at least the period when they are going to do the solar observations, say within 2 weeks, within 3 weeks or something like that. So that at DKIST they, they can have the proper configuration set up as well. You know, even the ALMA people are learning how to do solar because you know, they were going on their own. And for now, ALMA by itself, I don't think it has shown a lot. It sort of needs the support of complementary observations. But now they're learning and they can do it much more easily and so. IRIS is really not a problem. I mean, IRIS has been extremely helpful in all of this, has always observed every time that ALMA was observing. They are very flexible.
More questions, more comments? Go ahead, ask whatever you have in mind.
Dennis, this is really a cool paper, the one of Momo, right? Yeah.
Less of a question than a comment, but band 6 is a lot more complicated in my experience than most of the other ALMA bands in the chromosphere. I mean, in the Lukacheva paper, or no, the De Silva Santos paper, where they did the inversions with IRIS plus ALMA, they said that the band 6 had a nice narrow contribution function in log tau. So it was essentially just saying the temperature at this height is basically this, whereas in geometric height or in log column mass, which is what I did my inversions in, which correlates more closely with geometric height. The band 6 formation height is a lot more bimodal and a lot more complicated to disentangle. So that's just, you know, something to be aware of. What looks like a single height range in one height scale is actually much different in terms of geometric height. And yeah, it's just really interesting, the information, the extra information that you can get out from that. Like I've been seeing that it appears that the hotspots in band 6 form at a distinctly higher layer than the cold spots in band 6. And the calcium 8542 line is sort of sandwiched between. So yeah, interesting opportunities. If anyone else wants to try inversions in log column mass, I'd be happy to have someone else to chat and commiserate with that over.
That is very interesting, Ryan. Yeah. So that it seems like in a sense, you are confirming what Momo found for the band 3, that also, you know, in very hot spots it forms a certain place, and in colder spots it forms somewhere else with a large difference.
Yeah, with a very large difference.
It wouldn't be, it's not, guess it's not surprising until you get in the middle of the photosphere, really, or the temperature minimums or so. Because as soon as you get into these higher parts where ionization shocks and so on can change a lot the local environment, the amount of free electrons, essentially. That probably goes somewhere else. So
yeah,
nice.
if we can discuss this in the journal club that's right after the class. So whoever wants to talk about it, we can chat after us, because the paper about the fibers discusses this.
Oh, it does?
Okay.
Okay, more questions, more comments? Okay. Well, I actually just wanted to make one remark, because I was in an interesting discussion online with somebody who was a bit skeptical about the DKIST and who is from Iris team. I just want to say one thing, and that's there is a big advantage with the DKIST, is that it's going to be polarimetric telescope. So we will be able to see and measure all 4 Stokes parameters, which means we will be having direct access to the magnetic field. Now you all might have seen already through doing your homeworks and so on, that measuring your magnetic field is not so straightforward, and etc. But there is a whole new dimension opening up to you if you can do full Stokes polarimetry with your telescope. Yeah, and that really allows you to understand much more physics.
I shouldn't say this because I really don't understand it, but there is a possibility that you would measure magnetic field in the chromosphere with ALMA as well. You can measure polarization, and depending on the differences in polarization, I think, in different channels and so on, you can get an idea of the chronospheric field. Infer the magnetic.
Yeah. Yes. I imagine the radio telescopes can measure polarization relatively in a relatively straightforward way, because they are antennas, right? So they measure polarized light by default.
I don't think it was offered even in this next call for solar things. They do it for other sources, yes.
They take the linear polarizations by default, so that's all.
Can you speak up?
Recorded. They take the linear polarization by default. They haven't started any circular polarization.
Circular polarization. Mm-hmm.
Okay, if there are no more questions and comments, thanks Gianna again, and yeah, I will put this online as soon as possible. So yeah, we're gonna stay at this Zoom ID for our group meeting. I'm gonna stop.